So ladies and gentlemen, hello and warm welcome to all of you. My name is Zsigmond Pétot. I'm thrilled to be here today to kick off this exciting meetup event. Before we dive into the details of today's agenda, let me take a moment to introduce ourselves and the fantastic community we are a part of. We are part of the Google Developer Groups, or GDG for short. GDG is a global network of communities passionate about technology and innovation. These groups bring together developers, designers, entrepreneurs, and enthusiasts who are eager to learn, share knowledge, and collaborate on various projects. GDG communities organize meetups, conferences, and workshops, creating vibrant ecosystems where ideas thrive and connections are made. Today, we are gathered online as members of the GDG Cloud Budapest community. Our focus revolves around the vast possibilities of the cloud, specifically in the context of Google Cloud Platform. We have a diverse group of professionals and enthusiasts who are always exploring the latest advancements in cloud computing, sharing insights, and supporting each other's growth. One of the essential aspects of our community is our regular meetup events, where we gather to learn from experts, discuss trends, and showcase innovative projects. And that's why we are here today. We have a fantastic lineup of presentations and demonstrations prepared for you, centered around an essential tool in the world of cloud infrastructure, Terraform. Terraform, an open source infrastructure of code tool, empowers professionals like our speakers today, György, Olivér and Krisztián, to define and provision infrastructure resources. Today, they will share their extensive experience and insights on Terraform, focusing on its capabilities and limitations through an example application deployment called N8N, a powerful workflow automation tool. Throughout the evening, we will explore the journey from manual deployment to automation, reviewing the Terraform code and the continuous integration and continuous deployment pipeline. Our speakers will also provide captivating demonstrations showcasing cloud-native solutions and cloud security best practices. Now, don't worry if you are new to Terraform or CICD. This session is designed with a basic level of understanding in mind. However, some familiarity with Terraform and CICD basics will enhance your comprehension of topics. Remember, our community thrives on collaboration and knowledge sharing, so feel free to connect with the speakers and other attendees. Before we begin, I want to extend an open invitation to each and every one of you to join our GDG Cloud Budapest community. By becoming a member, you will gain access to exclusive events, workshops, and the opportunity to collaborate with talented individuals who share your passion for the cloud. Once again, welcome to this exciting meetup event. We hope you enjoy the presentations, gain valuable insight, and leave inspired to explore the endless possibilities of Terraform and the cloud. Thank you very much. Let me hand over the screen to the speakers for the presentation. Gentlemen, the floor is yours.
Thank you and welcome everyone. I'm so glad that so many of you showed up. My name is Krisztián Dobos and I am a cloud engineer at Deutsche Telekom IT Solutions Hungary. And I am here with my colleagues to give you the presentation about Terraform in Google Cloud.
Everyone and welcome. I'm Olivér Herceg. I have been with the company for almost a year. Currently, I have Google Cloud Associate Engineer and Google Cloud Professional Security Engineer certification. Sorry. When Gyuri asked if I wanted to join the terraforming of the NAN, I wanted to get involved. I knew it. So thanks again for the opportunity.
Hello everyone, my name is György Halasi, and just like my fellow presenters, I'm from Deutsche Telekom Hungary. I have been with the company for a year now within the Google Cloud Engineering team, and since this last year, we had quite a few interesting pet projects and proof of concepts, which one of them we would like to present today. So with that, I would like to step in with the first topic of our presentation today. And within this session or within this stage, we would like to give a short, brief summary on the story behind this work itself, how it came into the picture, and how we tackled it in our work activity. On top of it, we would like to share some of the Terraform export related findings and explorations that we had, and why we decided not to use Terraform export, even though it's already available within the Google Cloud integration. And last but not least, in this part of the session, I'm going to hand over the virtual microphone to Oliver to showcase the Terraform resource code itself. So no further ado, I would like to unzip the story behind this work activity itself. We had an internal customer request that they wanted to use an N8 application, as it has been mentioned by Zsigmond at the beginning. And we had no much idea about what this application is capable of. But after reviewing the documentation, we obviously realized that it's a workflow automation tool that can be hosted on any of the hyperscalers, even N8N as the company provides a paid service that they are hosting it on their infrastructure, but we decided to self-host it. So we created a proof of concept out of this idea, and the Google Cloud team win the opportunity, as this was the group which has been established by the latest within our organization. And we basically did a manual deployment at the beginning on Google Cloud Console by manually clicking over the resources and creating them one by one. And since it was the end of the year last year and the holiday season was just around the corner, we knew that we need to destroy some of the resources during the holiday breaks, just to be cost aware, of course. And with that, we had to redeploy the solution again and again and again. And as we know, in IT, we don't really like to do that. I think everyone in the audience can agree with this statement, that as soon as you can automate, just do it. So we looked into the automation possibilities. We quickly realized that Terraform was used within the company, and also at the time we had just received our certifications in the HashiCorp Terraform certification, so we wanted to test our knowledge in action. So basically, this was the story behind why we come up with this N8, and we had not much knowledge at the beginning about this application, but we wanted to make sure that we were able to test both of our knowledge in GCP as well as with Terraform. So how we started tackling this activity? We wanted to go with the lazy way, as most of the IT persons and guys like to do it. So we wanted to check if there is a possibility that the currently already manually deployed GCP resources, we can generate the Terraform code out of it without writing it ourselves. And the short answer is yes, there is a possibility. The longer answer is that unfortunately it has some limitations, and with that we decided not to use this. What are these limitations? Well, as you can see on the command that I'm showcasing on the screen at the moment, it's still in beta, so Google and HashiCorp is corporately developing it still. And the major limitation is that not all the resources are being supported at the moment. Even resource configurations are not supported at all time. And with that, it means our solutions cannot be fully exported in a bulk export or in a specific targeted export, even though it's not a brain surgery. So you can see from the command line, you can select the output directory where you want all the Terraform files to be created, and select the project. Even a folder is capable of managing it if you want to step one level up. But basically what it means that every resource that you already have in GCP within a project, that hopefully will generate a Terraform code out of it. Further limitation is that the Terraform code itself and all the variables and values within it are hard-coded or baked in to the code itself. So you either need to refactor every single variable in the code, and on top of it, you also have to import everything in the TF state file. Otherwise, you will find errors left and right during the Terraform apply or during the import process. That's because the redeployment of these resources are just unable to handle the naming uniqueness that is required by GCP. Some of you might be familiar that, for example, project IDs cannot be recreated until it has been deleted and waited for 30 days. So you have to have a unique project ID, and in that case, obviously, you need to have a different naming convention behind it. So with all these limitations, we decided not to play around with this solution, and instead we wanted to make sure that we can just write the code from scratch. And obviously we used HashiCorp libraries and modules, and we also used the template codes from the HashiCorp website itself that helped us to speed up the process. And the benefits of this whole infrastructure as code automation for us was the speed. So it was obviously just a one-click solution to deploy the whole N8N application on GCP. And the second thing was the consistency. So we did not make any mistakes during the redeployment by manually doing it. So these were the key elements and the key benefits that we had. And with that, I would like to hand over the words to Olivér to showcase you the Terraform code itself.
Thank you. So today I will be speaking about Terraform and the HashiCorp configuration language HCL, which are used for infrastructure as a code. Terraform is an open source tool that allows you to define and manage infrastructure resources across multiple cloud providers. HCL is a configuration language used by various HashiCorp tools, including Terraform, Consult, and Vault. It provides a simple and intuitive syntax for defining resources, variables, and data sources. So, in this speech, we'll be focusing on a code that deploys a containerized application on Google Cloud Run with a private HTTPS load balancer. The load balancer provides a way to access the Cloud Run service through an external IP address over HTTPS with an SSL certification managed by Google. The configuration includes several resources such as Google Cloud Run service, resource that specify the container image, environment variables, and resource requirements of the application. An IAM policy binding that allows all users to invoke the Cloud Run service. Additionally, private HTTPS load balancer is configured to route traffic to the Cloud Run service using a serverless network endpoint group. An SSL certificate managed by Google provides HTTPS encryption for traffic between the client and the load balancer. The configuration also uses various other resources and modules such as Google SQL database, Google Secret Manager, and vPXE access connectors. Overall, this Terraform code is a very good example of how to deploy a secure and scalable containerized application on Google Cloud Run with the necessary resources and policies to allow public access to the application. But before we dive deeper into the Terraform code, let's discuss some basics of HCL and Terraform. Like I mentioned at the beginning, you can define three things mainly: variables, resources, and data sources. Let's go through them. So HCL allows you to define variables and reuse them through your configuration files. Variables can be assigned values from a file or passed in from a command line. Resources are the building blocks of the infrastructure in HCL. They represent infrastructure components such as virtual machines, databases, or networks. Resources are defined using syntax, resource type, resource name, and needed attributes. Okay, let's go to the data sources, which are used to retrieve external data and use it within your HCL configuration. For example, you can use a data source to retrieve information about an existing VPC and use it to create a new resource within that VPC. Okay, so that's all about variables, resources, and data sources. Now let's go through the Terraform code together. Usually Terraform files are end with .tf extension. You have an option to separate your code into different files. For example, separate files for the network, database, etc. At runtime, Terraform we treat it like one big file, just like everything is now in the main.tf. For the presentation, we decided not to split the files, but put everything in main.tf, so I don't have to jump between files, so it's easier to follow what I'm showing to you. Okay, so let's start with the variables.tf. So basically, the content of this file is a variable declaration, the variable declarations. Okay, let's go through them. So you can find here the project ID, you can find here the bucket name, you can also find here the region, which will use the load balancer and the Cloud Run. You can find here also the zone, which will decide it where the resources will be deployed. You can find here the NAN admin username and also the password. You can define here also the DB username and the DB password, the SSL certification, the load balancer, even the support email, and also the latest digit. Krisztián, in the next section, we'll talk about how you can give values for these variables. So now let's jump to the main.tf. Okay, so I decided to make blocks, and I will start talking first about the provider. So This block of code used to define the Terraform backend configuration and the provider configuration. The first section of the code defines the backend configuration for Terraform to store its state Google Cloud Storage bucket. The backend block is used to specify the type of backend, which is GCS in this case. The bucket parameter specifies the name of the GCS bucket where the state file will be stored. The prefix parameter specifies the path inside the bucket where the state file will be stored. The credential parameter specifies the path to the JSON file containing the GCP service account credentials that Terraform will use to access the GCS bucket. The second section of the code defines the provider configuration for GCP using the provider keyword, followed by the name of the provider, which is Google in this case. The project, region, and the zone parameter are set to the values passed in the variables. This configuration set up the GCP provider for Terraform to be able to interact with GCP service and resources. Okay, let's jump to the next one, which called Enable APIs. So this block enables several APIs for the GCP project using the Google Project Service resource type. If these are not enabled, the services will not run. These APIs are IAP, Cloud Run, VPC Access, Service Networking, and Resource Manager, and the Cloud SQL. And here, the disable destroy parameter is set to false to ensure that APIs are not disabled when Terraform configuration is destroyed. So let's jump to the next part, which is the secret manager. Okay, the provided code here is used to create and manage secrets in Google Secret Manager. The Google Secret Manager is a service provided by GCP and it allows users to securely store and manage secrets such as API keys, passwords, and certificates, and many more. So here, the first section of the code creates a secret in Google Secret Manager for the Postgres password using the Google Secret Manager secret resource type. The project parameter is set to the value is passed as a variable, and the secret ID parameter is set to db Postgres db password. The replication block is used to specify the replication settings for the secret. The second section of the code creates a new version of the Postgres password secret using the Google Secret Manager secret version resource type. The secret parameter is set to the ID of the previously created secret, and the secret data parameter is set to the value passed is in the variable. This resource type is used to add a new version of the secret, allowing users to rotate their secrets and maintaining security. Here we are doing the same, but for the NAN authentications. Okay, let's jump to the next one, which is about VPC networks, global IP, and private VPC connection. So let's go through them. So this part, so this creates a new VPC network named NAN VPC. The next one, this set up a VPC access connector named NAN VPC access connector. This connector enables VM instances in your VPC network to communicate with internal Google service using internal IP address rather than external IP address. The compute global address, this creates a new global internal IP address named NAN VPC IP range with an IP address 10.195.176.0 and the prefix length of 20 bits. This IP address is used for VPC peering. Google Service Network Connection. So this set up a new private service network connection between the VPC network and the Google Service Networking API. It also creates the reserved peering range associated with the VPC network. So overall, this resource work together to provide secure and private communication between resources in VPC network and internal Google service. So let's move on. Cloud SQL database. So here, this long block. Just a moment. Okay. So this Terraform code provisions a Cloud SQL database instance with a Postgres SQL database engine. The resource is created using the Google SQL database instance resource block with various configuration options set in the setting blocks. The Google SQL database resource block creates a database name NAN within the instance. The Google SQL user resource block create a users with the provided name and password and attach it to the instance created in this Google SQL database instance resource block. And finally, there is a dependency on the here. And finally, there is a dependency on the Google Service Network in connection VPC connect resource, which create a private connection between the Cloud SQL instance and the VPC network defined in the Google Compute Network resource block. This ensures that the Cloud SQL instance is only accessible from within the VPC network. Okay, let's move on to the IAP section. So these Terraform resources are used to configure identity-aware proxy, or call it IAP, for a project. The Google IAP brand resource creates an IAP brand, which is a configuration object that specifies how your application will appear to users when they access it through IAP. The support email argument specifies the email address this user can contact for support related to the application. The application title argument specifies the name of the application that will be displayed to the users. The Google IAP client resource creates an IAP OAuth client. This resource is used to authenticate and authorize access to resources behind IAP. The display name argument specifies the name of the OAuth client that will be displayed to the users. The brand argument specifies the name of the IAP brand that client will be associated with. These resources are useful for securing access to web application deployed in GCP by allowing you to control access based on user identity and access policies. So let's move on to the next one, which is the external HTTPS load balancer module. So basically, this Terraform code set up an external HTTPS load balancer using a module from Google Cloud Platform provider. It also creates a serverless network endpoint group to use by the load balancer here. The module block specifies the source for the module and passes in the required variables. The backend blocks define a default backend with the IAP configuration to enable identity-aware proxy for the authentication. The Google Compute Network region network endpoint, the group resource, is set up a serverless network endpoint group, which represents a group of cloud run services that can be used as backends for the cloud balance to the load balancer. The cloud run block specifies the cloud run service that will be used as a backend. Okay, let's move on. And here we are at the Cloud Run. So Cloud Run is basically the soul of our project. This Terraform script provisioned a Google Cloud Run service and an associated serverless endpoint network endpoint group, as well as set up HTTPS load balancer with an IAP authentication. The Google Cloud Run service resource create a Cloud Run service named any application, which is configured to use a specified Docker image here, using this Docker image, and has several environment variables set, including database connection details and basic authentication credentials. The secrets we created in the secret manager are given a role here, and we will explain later what the difference is if you just pass them as a plain variable. So here we are getting this value from the secret manager. The Google Compute Region Network Endpoint Group resource create a serverless endpoint group that points to the Cloud Run service created above. The module LB-HTTP resource creates an external API load balancer with the IAP group, which has provided authentication. The load balancer in the backend is set to the serverless endpoint group created earlier. The traffic was directed to the singular revision here, not shared between multiples. And we made it mandatory to wait until the required API is mounted. And last but not least, here the disable auth. So this Terraform code disables authentication for a Cloud Run service. The Google Cloud Run service IAM policy resource is used to apply the Google IAM policy data to the Cloud Run service IAM policy. The data.google IAM policy resource retrieves the IAM policy data for the Cloud Run invokers roles, which includes all user members. The user member represents any user of or service account, so granting it with the specified roles with this, or to allow anyone to invoke the Cloud Run service without authentication. It's important to know that this approach should be only used in specific situations where you want to allow unrestricted access to the service. In general, it's recommended to secure the Cloud Run service with authentication and authorization mechanism, so as identity-aware proxy or OAuth 2.0 to prevent unauthorized access to your application. In our case, this was necessary because we put the Cloud Run behind the load balancer, and the way to make the application available was this. We used IAP to solve the authentication. So basically, that was my part. I hope you find it interesting, and there was some useful information for everyone. Thank you for your attention, and I would like to hand the floor over to Krisztián.
All right, so I'm going to mainly talk about the CICD part and the CICD pipeline part of the project. So we basically hosted our project on GitLab's CI/CD pipeline solution, mainly because that's standard at our company. Everyone else used it, so we decided to go with it as well because it functions perfectly fine for our requirements. It's designed to communicate neatly with cloud solutions, including Google Cloud, and has some neat resources that help with the deployment. So for anyone who is not familiar with GitLab, GitLab is basically a DevOps development and operation software package. It offers a wide variety of things, but we mainly used its code repository and CI/CD solutions. Basically, what CI/CD stands in GitLab's vocabulary is continuous integration, continuous development, and continuous deployment. So one part is the code repository. The code repository is basically works the same as GitHub's code repository, which you're probably more familiar with, but it's basically the same thing. It offers everything that a Git supported repository should give you. And the other part is the pipeline itself. And I will talk about how to construct a CI/CD pipeline and how we solved the update management of the pipeline and the infrastructure as well in this part of the talk. So here is how the repository itself looks like. As you can see, it's very familiar for anyone who used GitHub before. Basically work the same. The only difference is that here you can run CI/CD pipelines. I'm going to explain what a CI/CD pipeline in just a second. But the main thing is that every pipeline requires a YAML file named .gitlab-ci, and if your repository includes this file, then GitLab automatically will recognize it as a pipeline and treat it as such. Right. So what is a GitLab CI/CD pipeline? It basically the top component for the continuous integration and continuous development and deployment solution of GitLab. On a pipeline, basically, you can configure and run different jobs that fulfill everything you need. Every pipeline is set up from stages. So every pipeline has multiple stages. You can make the stages independent for each other. You can make stages that depend on each other, so they run one after the other, and you can set up parallel stages as well. So you can run two stages at the same time, and every stage has one GitLab runner which composes the jobs, basically the code that you want to run, and you need this YAML file to set up the structure of the stages and then to configure what exactly should run on these runners. There are two types of runners. There is a shell executor, which basically just runs shell commands, but you can use Docker images as well as the base image for these runners. And in that way, you can use pre-installed libraries. So you don't have to spend hours to install every single shell library or Python library or whatever you're using to finish your job. And for that, you need Docker. And one little thing to note about GitLab runners is that they are running on a Docker-based system, so they are speeding up Docker image every time when you're using base image to run a job. And one of the biggest issue I had with this GitLab CI/CD solution is that natively you can't really use Docker commands when you start a GitLab job, so you can't really download images and can really interact with other repositories, for example, Google's image repository as well. You need GitLab's Docker in a Docker solution for that, which basically uses the Docker, the outside resource that runs the GitLab runner, and you can use from the outside resource the Docker commands inside the GitLab runner. But to achieve this, you have to go outside of the scope of the runner, which is sometimes not allowed. For example, within our company, it's disabled. So I had to spend a great deal of time until I realized that. So one thing I can recommend if you want to use Docker commands and Docker images within a GitLab runner is to always make sure that it's turned on. Yes, and I'm gonna go through how this whole CI/CD pipeline is set up. Basically, for those who don't know what a YAML file is, YAML stood for yet another markup language, funnily enough, and it later was changed to YAML ain't markup language. So it's basically a markup language, but it's data oriented and not document design oriented. That's why it later was changed to ain't a markup language to make this distinction. Basically, here you can define different structures, and within inside this CI/CD, GitLab CI YAML file, you can define the exact commands you want to run inside every stage and every job. Yeah, and other thing that you should know about these jobs, that they are individual instances, and whenever you start a pipeline, they start and stop within the pipeline, so you cannot interact with these jobs outside of the pipeline. So everything defined inside the GitLab CI/CD file, that's all the interaction you can have with these GitLab runners. So you have to make sure that no command requires a manual approval, because you cannot approve anything after you started the pipeline because they are non-interactable. And I'm going to show how this markup YAML file is set up, or our YAML file is set up. So this is how usually a CI/CD pipeline looks like. At first, you have to define the stages. You can name them anything, so this is not relevant for GitLab, so you can name them whatever. It's just for ease of readability. You should name them according to what their purpose is. You can set up as many stages as you want. You can set up test stages, build stages, update stages, whatever you want. As I said, you can play around how the stages are dependent or non-dependent on each other. Just be careful, because if you don't set up the dependency correctly, the pipeline might fail if you require resource from a previous stage in a later stage and the dependency is not set up correctly. So always be mindful of how the stages are dependent on each other. Then you can define basically functions in this code blocks that you can reuse using this configuration, which then you can reuse in every stage the same. So it supports reusable code between the stages as well. And yeah, the way you set up a stage, basically, you define a block. The block name can be anything. It doesn't matter, just again, name it according to the purpose of the block. You have to define the stage where this block has to run. And if you want to use an image from a Docker image repository, then you can define it here under the image. There are a lot of other configurations and setup that you can include here. You can set up variables, secret management, and a lot of other stuff. But for our project, we didn't require it. Here we are using Google Cloud's, one of Google's made Docker image, which includes Terraform and the Cloud SDK. We need Terraform for obvious reasons, and we need the Cloud SDK to communicate with the Google Cloud, so we can send comments basically to the Google Cloud console and authenticate ourselves, request data, etc., etc. And after that, you can set up before script, and you can set up after script as well. So basically, you can divide your code blocks where the commands, the shell commands run, into different parts within a stage. There is no obvious reason why you need to divide them to before script, and after script. This is again just for readability's purpose. It's easier to manage the code when you make it obvious which part of the commands have to run when. And right, so before anything happens, first of all, we authenticate ourselves with gcloud, with the Cloud SDK, with this gcloud command, and we use a credentials file or a variable, environmental variable that we created here in this prepared credentials block. Within GitLab, you can do secret management and environmental variable management as well. So you can set up secrets within GitLab, and then you can ask for these secrets or environmental variables or whatever within any job. You can disable it as well. So if you don't want a job to reach environmental variables for whatever reason, then you can disable it on that specific job, so it can't reach your pre-set up environmental variables. But in this case, we used it to store our credentials files to Google Cloud. Of course, you could use different methods of authentication as well. You could use Google Secret Manager and authenticate yourself through that. GitLab is capable of authenticating to cloud services with JSON, HTML, or HTTP headers as well. So you could authenticate like that, or you could use a local secret management service as well. So your hands are really not tied on how you set up your security in this regard. But we use the simplest and most obvious solution, mainly because this is an in-house project with few people using it. So we didn't want to create a big operational overhead with a really complex and really secure secret management. But of course, more security can always be applied. And the other thing that happens here is we create a bunch of environmental variables, all named TF underscore var underscore blah, blah, blah. The reason why we do this, because as Oliver talked about, Terraform can use variables, and there are actually different methods of creating and using variables within Terraform. And one method is that Terraform can recognize and can use environmental variables within your environment. The only requirement is to start the variable's name with this uppercase TF underscore var underscore. If you name your variable like this, then Terraform will automatically recognize it as its own variable. And if you set up the variables correctly within Terraform using the Terraform variable module, then you can just grab these, or Terraform will just grab these variables and use their content. So this is the easiest way and most readable way without jumping into different variable and whatever files and looking around where a variable is defined to set up some unique information. Here we save the bucket name where the Terraform state file will be created, the project ID, the project number, etc., etc., etc. And we also exported out the N8Ns where our N8N image is hosted on Google Cloud, so we can use it when we build our infrastructure. So that's basically what happens here. And then we run the script itself. First, we check or basically digest the latest image on the Google Cloud image repository. So we always want to use the latest image. The image that hosted here is ours, so we upload it there, not N8N. This is not an N8N managed repo. This is our repository. Basically, how we handle updates is to download or ingest the latest image into our own repository and use that image every time. And the reason why we do it like this is to make sure that we always use the latest image up there. The simple way to do it is you can send a request to the Cloud Container Images to list out every image. We could request the format to list it according to its unique identifiers, and we can limit them to just one. And because Google automatically lists these images according to their creation time, so the newest gets listed out first. So if we limit it to just one, then it always lists just the first image, so the image that was created or uploaded the latest. So in this way, we always just digest the newest one. And then we basically just check if the main.terraform actually exists to make sure that we don't run into bugs when accidentally something got deleted. We run the Terraform initially is it command, so Terraform starts running. This was for debug purposes, so it's not important. This is commented out, as you can see. And we run Terraform apply. And as I said, the runners are non-interactable, so we have to auto approve. Otherwise, if we didn't include this part, then Terraform would request a manual approval. The reason why it requests is because when you run Terraform apply, it automatically lists out every changes that it's gonna make in the infrastructure. Every new resource it will create, every resource changes. And Terraform wants to make sure that you go through all of it, see if no unnecessary resources are being created or important resources are being deleted. And if you find everything according to your needs, then you can manually approve it. But since GitLab doesn't allow us to manually approve it, then we have to automatically run it. You can set every stage running to events. Automatically, your whole GitLab CI/CD pipeline runs every time you upload to your code repository. So every time you do a git push, it runs. The way you can turn it off, you can either connect it to an event. So you can write a cron job. There is a scheduler on GitLab as well, and you can run your pipeline every week, for example. Or you can set up some other event. There is even a webhook solution on GitLab, so you can even set up some kind of code that ingests some information from the web. For example, the version number of the N8N image. You can compare it if your N8N version is different from the one on the N8N's GitHub or Docker or wherever you're downloading the image from. And if the version numbers differ, then you can set up an event to run your update pipeline. Yes, and the reason we didn't separate build and update to two separate stages is because the way Terraform works is that it only touches resources that you change. Terraform sets up a state file, and within that state file, it lists out every resource and every part of every resource that it has access to. And whenever you run Terraform apply, it basically checks the actual state of your infrastructure and its TF state file. And if there are differences between the two, then it will make those differences disappear. So for example, if a resource is missing in the TF state file, but it exists on your infrastructure, then it's going to delete that resource. And the other way around, if a resource doesn't or exists in the state file but doesn't exist in reality, then it will create that resource. And so that's how Terraform operates. So, and because of that, it's not necessary to set up a separated update stage for our purposes, because the build stage won't touch anything that it's already there and it's inside of the TF state file. Therefore, we can run the build stage even if we just want to update the image version of the N8N image, M8N Docker image, because in that case, it will only see difference in the Cloud Run, the service that hosts N8N on our Google project. And it will only stop the Cloud Run, it will change the image to the correct one and restart Cloud Run and won't touch anything else. So there is no real necessary to create a separated update stage. But of course, if you don't just use Terraform or you have some specific needs for update or whatever, because Terraform, of course, doesn't support everything. So sometimes you have to set up different things or you have different needs for update, then it makes sense to create a separated update stage. But in our case, the build stage basically is capable of performing the update as well without any unnecessary changes in the structure or destroying or creating resources. And we have another stage which will destroy almost every resource, which basically is the same as the build stage. The only difference is that here there are two differences actually. One is that here we run the Terraform destroy, which basically what it does is to delete every resource that's in the TF state file. So it basically does the reverse of apply. So in that way, we can automatically turn off basically everything and remove everything from our cloud, and it will stop accumulating unnecessary cost if we don't want to use our N8N solution. The only difference between this code and this code is this line, because as I said, Terraform doesn't support everything. There are limitations to it. One such limitation is this identity aware proxy, which requires this identity aware proxy brand, which will György talk a little bit more about later. And the problem is that Terraform actually supports to create this IAP brand resource, but it does not support the deletion of it. So if we didn't include this line, we would run every time that if we run this script, we run the destroy script, it will destroy every resource except this IAP brand from Google Cloud, and it would remove every resource, including the IAP brand, from the TF state file. When we run the build stage again, it would see that it will want to create the IAP brand because it's not in the TF state file. It thinks that nothing exists, no resource exists because it's not in the TF state file. But because we run the apply command, it wants to build the IAP brand. But the IAP brand already exists, and there is a difference between TF state file and the actual infrastructure, a difference that Terraform cannot comprehend because it thought it removed this IAP brand, because here we destroyed it, so it thinks that it's removed, but it's not. So the whole pipeline will fail because of this discrepancy. So one of the way that we could solve it, one way is, of course, is after every time we run the distro, we go in Google Cloud and manually remove this IAP brand. But of course, that's not a very comfortable thing to do. Every time an extra step basically that we have to do. Yeah, and basically with this way, we import this IAP brand into our Terraform state file, and that way we remove this discrepancy, and the whole pipeline is gonna work. So that's about it from me. So I'm gonna pass the ball back to György to finish this off.
So regarding cloud nativity, why we are thinking that this is part of the cloud native solution. We, first of all, as the colleagues showcased, we are utilizing Cloud Run, and most of the Google Cloud services which we are used are Google managed, including the service key management and the rest. And with that, this solution is scalable and can be redeployed at any time, and it's not necessarily associated with user count, so you can increase the Cloud Run environment or the hardware specification behind it at any given time. As you were able to see that we are loading all the traffic 100% on one revision at the moment, but there could be that we are testing A/B testing or green-blue testing the solution. And with that, I would just want to showcase how it looks like in practice. So in Cloud Console, you can see that we have created the Cloud Run application, the N8N app, and you can see that we deployed it in the Europe West 1 region because it was the closest to us with the least amount of latency and the associated network costs. The authentication set to unauthenticated, as Oliver mentioned, and what is important is the ingress control because it has been set to internal and through the load balancer. With that, you can check quickly the revision state. We've used one instance at this moment on port 5678, and it's using the image URL that has been set from the container registry. We have built the image ourselves through Cloud Build, and basically limited all the resources to minimize cost at the moment. So as you can see, it only runs on one CPU and with 512 megabytes of RAM. And with that, I would like to deep dive into the cloud security, but I would try to make it short. So what we thought that is important is to ensure that service account has the least privilege access. We limited it to the permissions that only allowed the Terraform code to deploy and the services on GCP. As it has been mentioned, we've turned on the identity-aware proxy to limit unauthenticated access to the service itself, because we wanted to make sure that it's kept within our premise. We applied domain restricted sharing because we wanted to make sure that it's even, locked down further, and only within our GCP organization domain address we can access this service. And as we mentioned, we applied networking risk control and secret management, which I would like to show in a bit. Starting with networking risk control, the N8N application, when it spins up in Cloud Run, creates a URL. It's publicly accessible unless you locked it down behind an IAP, and this is what we are seeing. So on the top, you can see the public URL, but if you try to visit it, you will encounter an error page because of the internal HTTPS load balancer ingress control setup and configured correctly. Domain restriction sharing, not too much to show here. The only error message that you will see is that you are not within the organization, and that's the reason why it denies you, even though you entered your correct credentials and authenticated through IAP. If you don't have the necessary IAM permissions, you will also encounter an error message. This is after authenticating through the IAP correctly, but you still have limited IAM permissions, then you will face this error stating that it's unavailable for you. And last but not least, how you can access them. Well, you have to give the Cloud Run invoker and the two IAP secure tunnel user and web app user role to the specific user in order to go through the IAP authentication and finally reach the point where you land on the administrative welcome page on the N8N application. One thing to mention here is that you can see we have reserved the front-end IP. That's what you can see, and we played some wizardry with the NIP.io ending just to make sure that we can apply an SSL certification on this IP domain. Otherwise, you would need a regular domain name in order to do that. So with that, the last thing is the secret management. As it has been mentioned by the colleagues, there were two variables that we wanted to pass to Terraform, but we wanted to make sure that in case any of the internal colleagues have a viewer role on the Cloud Run and they can check the revision, that's on the right side. You can see that all the environment variables are listed as free text except the two at the bottom, the PostgreSDB password and the basic authentication password. These are coming from the secret manager from Google itself. So with that, the secret manager can be locked down unrelated to the Cloud Run viewer role itself, which means that unnecessary access can be controlled and will not be visible for those who might not necessarily need to have access for this information. So these were the basic security elements that we thought that necessary to apply outside and inside of our corporation in order to comply with the least amount of basic security configurations that we had. And I think it's time to Q&A. So I would like to give the floors to the questions. And I think I can answer the first question, which was associated. Are there any enums in Terraform for predefined zones, types, and instances, for example? Yes, there is. It's called, within Google, it's called Google Compute Zones, I believe. It's a data type, a data source type that basically goes and loops through all the available zones within a specified region. And with that, you can use it as a variable within Terraform to actually use the zone that you defined. Otherwise, you can just define it directly within a variable name.
Sorry, I want to add a little bit to this, that within Terraform, there is a validation block called validation that you can include into any resource block. And within that validation, you can set up checks, which are really similar to an enum type of file as well. So you can use that as well.
Yes, thank you. Second question, is there any efficient way of handling variables in Terraform? Could the variable be shared between multiple configuration files? Oliver, do you want to answer that?
Yes, thank you. Yeah, so basically there are several ways for handling variables and sharing them between configuration files. You have different approaches. For instance, you have input variables, you have module inputs, data sources, and also you can use the remote states. I recommend to read the documentation for more details. But the answer is yes, you can share it and you have several ways to handle it efficiently.
Thank you. Actually, there is another question related to the remote state. Do you want to answer that as well? What is the advantage of using remote state and secrets in cloud over GitLab's built-in state and secret handling?
Okay, so basically, secret management in the cloud, it provides, I think, better scalability, security, collaboration, and automation capabilities compared to GitLab and other options, in my opinion. But if you have something to edit, please let me know, guys. But this is my opinion.
Yeah, I think I covered the secret management part. So in case you want to control separately who has access to any of the environment variables, then you can do that within Google Cloud Secret Manager. Regarding the state, I think it was general practice from Deutsche Telekom that we are storing the state files in GCP as well instead of utilizing the GitLab's solutions. And there was one question that I think, Chris, you can present on your screen. Could you show how you hand over the project ID into a Terraform main TF? So basically, we need to present that we are picking it up from GitLab CICD as a variable. We are passing it into the YAML through to the variable TF file in Terraform. And from the variable TF file, it's picking up to the main TF, right? That's the flow of the project ID, I believe, but you can show it on your screen if you would like to.
Basically, all we do is to, if I understood the question correctly, then all we are doing is storing, but I'm going to show Visual Studio again. So we are storing the project ID within a GitLab variable, and that variable is basically accessible as an environmental variable inside every runner, every GitLab runner, except if you turn off the accessibility. You can turn off on the variable, so you can make a variable not readable by GitLab runners, and you can turn off the reading of environmental variables on the runner as well. But if you don't turn off either of it, then it's basically just accessible as an environmental variable, and you can just pick it up like that. So that's basically it.
And if you can just jump quickly to the variable TF, then you can see that the project ID has basically a placeholder where this variable has been passed, and then from the variable TF that can be picked up from the main TF. If you have it readily available.
Yes, I'm having it right here.
And you can just search for the project ID.
Yes, and
Has to be on the top.
Here it is, yeah.
That's on the top.
So basically, you just have to set up this variable block. So Terraform will look for this variable, and then we exported this into this, as I talked about, this tf_var underscore. It is the project ID. Under environmental variable. So because this block exists and it's named project ID, and this environmental variable exists named tf_var project ID, Terraform will connect the two together and will be able to use the variable of the project ID.
Yes, we hope that answered the question, whoever was posting it. Thank you. I think this was the last question that we had in the session. So I will hand it back to Camila.
Okay, I see one hand.
I just have one question about how are you managing the different environments in Terraform? Like you want to distinguish between staging, testing, or production environments. So did you distinguish between them?
Thank you for the question. I think I will have my answer, and then I will let the other colleagues answer as well. So since it was a POC, we can truly and transparently say that we haven't thought about managing different environments, but we had other customers within the corporation where we had to do this, and basically the separation happened during the GitLab CI. So based on the environment variable, in which production or testing or development phase you are working. It picked up the right stage, so it was handled by different branching of the repository code itself, and then that pushed the correct environment variables to the CI itself.
Okay, I don't see any more raised hands, so thank you from my side, and I hand over to Zsigmond.
Thank you. Thank you everyone for being part of this event. I would like to extend my deepest gratitude to our fantastic speakers, György, Olivér and Krisztián, for sharing their expertise and delivering such insightful presentations. I would also like to express my appreciation to all of you, the attendees, for joining us tonight. We hope you found the discussions engaging and the demonstrations inspiring. Thank you to the GDG Cloud Budapest community, including our community leaders and volunteers, for organizing the event. Furthermore, I would like to express our gratitude to Deutsche Telekom IT Solutions Hungary for their support in making this event possible. As we conclude this meetup event, I want to emphasize once again the importance of joining our GDG Cloud Budapest community. By becoming a member, you will continue to have access to valuable resources, networking opportunities, and future events just like this one. Let's keep the conversation going and together build a strong community that drives innovation and growth. On behalf of the GDG Cloud Budapest community, thank you for being a part of this event. We hope you leave with new insights and fresh inspiration. Have a good day, and we look forward to see you at our future events. Goodbye, take care.